What we've done is we've added matrices together, we've multiplied them by scalars, by numbers, and we've multiplied matrices together. What about division? Okay, now we're going to have to come at division from a different angle, and so we will. So the first thing is, what does a matrix do? So a matrix sends a point on the plane to other points on the plane. So for example, if I take the matrix 1, 3, -1, 4, and consider the point, let's say 1, -1, where does it send this? So let's do our analysis of the multiplication. This is a 2 by 2. This is 2 rows, 1 column. Those middle numbers match. So you can multiply these. Now the vector, the 1 -1, you multiply it as if it is a matrix. So we're going to get a 2 by 1, which is like a vector. So we're going to get 2 rows, 1 column. And how do we do this? We look at what row, what column we're in each cell, and we multiply that row in the first matrix by that column in the second matrix. So up top you got row 1, column 1, and this is row 2, column 1. So row 1, column 1, 1 by 1 is 1, plus 3 by -1 is -3. And on the bottom, -1 by 1 is -1, and 4 by -1 is -4. So we end up with a vector. Now it's written as a fraction, but it's not a fraction. -2, -5. Okay. So what we had here was we had a point, 1 along the x, -1 along the y. Let's draw that here. 1 along the x, -1 along the y. And it got sent to -2 along the x, -5 along the y. So multiplying by this matrix brought you from here to here. Now here I'm saying that the matrix A, for example, is 1, 3, -1, 4. So we're going to see, is there possibly such thing as the inverse of a matrix that will send the point back from where it came? So if A sends say point 1, -1 to -2, -5, whatever A inverse is, it should send it back. Okay, now there's one thing we should point out at this stage, that if you have a matrix that sends something non-zero to 0, missed. So say this is just some vector v that is sent to the vector 0. Now vector v just means a pair of numbers in the plane, and the 0 vector is just 0, 0. So suppose this is some matrix B. We'll see this again, but no harm looking at it now. Could it be possible to send back here? And the answer is no, because like if you take any matrix, so this question mark matrix, let's just call it C for a moment, but C, so C times the vector 0 should bring you back to V. So C times the vector 0, question mark, bringing you back to V is impossible, because any matrix by a 0 matrix, it gives you 0. But C0 is equal to 0. So if a matrix sends something to 0, you will not be able to find its inverse. Okay, so here we got some stuff. So if you hit a point with A and A inverse, the point goes nowhere. So what I'm saying is start at the point, say here, say this point here. So if you start at a particular point, let's call this vector u, say. So if you do AU, so that will take you from here to the -2, -5, and then do A inverse. That'll be the same as doing nothing. Okay, now the matrix that sends a point to itself, so this matrix sends U to itself, this is called the identity. Okay, and certainly for 2 by 2s, the identity matrix is 1 0 0 1, and it's like the number 1. Okay, because that's like what multiplying by number 1 is, it does nothing. Similarly, you have the 3 by 3 identity where it's 1s along the diagonal and 0s everywhere else. Okay, so looking from above, if you have a matrix and its inverse, it is the case that a matrix times its inverse is equal to the identity. Now you also require that it goes the other way around. So like think of starting say here. And the question is, how do you undo A inverse? So what is the inverse of A inverse? So if you go from -2 -5 to 1 -1, that's by multiplying by A inverse. How do you undo that? What is the inverse of A inverse? Well, that's going to be exactly the same as A. And what that means is you have that A inverse times A is also the identity. Now, not all matrices are invertible. So we kind of referenced this above. Any matrix that sends a vector to 0, for example, B here sends a vector V to 0, cannot be invertible for the reasons in light blue. So let's look at a particular example of this. So the matrix, say, there's different examples. I just want to see what picture I use. Okay, yeah. So let's look at the matrix of 1s. So the matrix of all 1s. Now this is not like the number 1. So it's not similar to the number 1. These things, these identity matrices, are similar to the number 1. This isn't. Now what we're going to see is that this obviously sends 0 to 0. So we won't actually multiply this out, but 1 1 1 0 0 is sent to 0. Now that's fine because it's not sending a non-zero vector to 0. It has to send a non-zero vector to 0 for it to be a problem. And we're going to show that it sends 1 minus 1 to 0. So let's look at 1 1 1 1 minus 1. Now I probably don't actually have the space to go through it. We'll do some of it because it's good for you to do this all the time anyway. So 2 by 2, 2 by 1, those middle numbers match. So I can multiply these together and I'm going to get out a 2 by 1. Now I won't cell this up because I don't really have the space. So I'm just going to write it like this. And so it'll be this, the top one here will be row 1 by column 1. 1 by 1 is 1, plus 1 by minus 1 is 1 minus 1 is 0. And similarly, the bottom is 0 as well. So this matrix of 1s, we'll draw this picture on the next page, is not invertible. Okay, now if you're just working with real numbers, every non-zero number has an inverse. So, for example, there is a number 3 inverse, which is just equal to a third, such that 3 by 1/3 is equal to 1, which is the same as 1/3 by 3. So this is just about division. And in real numbers, you can divide by every non-zero number. So this is just a fancy way of saying can divide, because that's what division is, inverting multiplication. Can divide by any non-zero number. You can't divide by 0. If you want to find out more about that, I may or may not. Maybe I'll just send you something, a little blog post explaining why you can't divide by 0. And then the question is, what is this the special number 1? We're missing actually something about the identity matrix, which we'll have to get back to. Oh no, we're going to look at it now. So this 1, like if someone asks you what is the number 1, It's the number such that if you multiply 1 by anything, you get the same thing. That's what the number 1 is. That's what's special about the number 1. And we have a similar story for matrix multiplication. I don't know if I have space here. So if you have any matrix A times the identity gives you the same matrix back, and it doesn't matter what order you multiply it. So the identity matrix is very much like a number 1. And what a number 1 is, it's a number you multiply anything by and you get the same thing. Okay, so what have we got here? So we haven't said how you actually could possibly invert matrices, but we said the big thing is certainly, unlike numbers where as long as you're non-zero you can divide, it's not the case for matrices. There are non-zero matrices, such as the matrix of 1, that you won't be able to, that don't have a multiplicative inverse. Now, we're not going to actually be able to say divide, and we'll explain why soon. So the thing up above here, there are, let me write. Oh man. Don't need this shit now. Okay, we're back. So now divide is going to be dangerous. Let's just say for matrices, you won't, like say you take a matrix and you multiply. See, there's basically, okay, I'm going to write something and I'm going to scribble it out afterwards, okay? So take a matrix A. Let's just actually do this. So I'm going to write this, but I am going to scribble it out again. So you don't have to take it down, but just kind of understand what's going on. I'm going to go quite quick. So take a fixed matrix, say 1, 2, minus 3, 7 for argument's sake. Now, so this is say our matrix B. And let's take another matrix A, which is say minus 2, 0, 1, 5. Now, unless I'm very unlucky with this, if you take the matrix B, just take the matrix B, 1, 2, minus 3, 7, you can multiply, you say, oh, I'll multiply it by A, but okay, say you multiply it by A, so this is B here, and say you multiply it by A, minus 2, 0, 5, 1, like this, and what do we get? So I'm going to do this quickly. So you're going to get minus 2, you're going to get minus 4, you're going to get 2, and you're going to get 17. So you multiply B by A and you get this matrix over here, which we call AB. Now, what about, and this isn't a concern for numbers because it makes no difference, but what if I multiply, instead of multiplying on the right, so let me call it like multiply by A, excuse me, on the left, versus multiplying by A on the right. So this is the matrix B here, and this is the matrix A. And if I multiply this out, and as long as it didn't go over, yeah, it should be okay. So we get 8, and the next one is 2, next one is 6 plus 35 is 41, and the next one is 7. And note that these are not the same thing. Now what that means is that multiplying by A on the left is different to multiplying by A on the right. And basically it follows in kind of a similar argument that you won't be able to talk about just dividing by a matrix. Because, and we're going to presumably see this, so we're going to see this somewhere else? No, we're not. Basically it's down here. Oh, we are going to see it. Okay, we will see it a bit later. Actually dividing is multiplying. Like if you want to divide by 3, you multiply by 1/3. And we're going to have so you multiply by if you want to divide by 3, you multiply by what's called the multiplicative inverse of 3, which is 1/3. Now, at real numbers, it doesn't matter if you multiply by 1/3 on the left or by 1/3 on the right, you get the same answer. So you can just say divide. But if the order of multiplication matters, there's a difference between dividing on the left and dividing on the right. In other words, multiplying by the inverse on the left or multiplying by the inverse on the right. So rather than talking about dividing at all, which is kind of complicated by on the left or the right, we're going to say multiply by the inverse. And we're going to recognize that when you're working with matrices, it matters if you multiply on the left or the right, you get a different answer. So we're going to use the language of not dividing but inverting. Okay, so that's what we'll get to. Because the problem is dividing matrix A divided by matrix B is not enough information to specify something. Okay, so as promised, we will rub this out. It's probably a quicker way of this, but yeah. So so we wrote on the previous page, can divide by any, well, now we'll use the language of invert, cannot invert any invert or undo, and the undo means undo multiplying by a matrix. You cannot invert or undo every non-zero matrix. Now what I want to say, and it's wrong, is you can't divide by every non-zero matrix. Right, so for example, we had the matrix of ones, which I'm going to call J. So let J be the matrix of all ones. That's a notation. Now you won't see it in anything you'll be looking at. So the matrix of all ones, like all matrices, sends 1 to 1. And it also sends 1 minus 1 to 1. So note that the matrix of 1 sends 1 minus 1. How can you send back from the origin? And you can't do it as we explained on the previous page, because the 0 vector by any matrix is just the 0 vector again. So basically what I'm saying is, like, say this blue thing, let's say this is J inverse, and you want to say that J inverse times 1 minus, times 0, 0 goes back to 1 minus 1, but it's not possible because, but this is just repeating what we wrote in the previous page. J inverse, if it's a matrix, times 0, 0 must go to 0, 0. You cannot get back, is the story. So the next question is, now we still haven't said how to calculate the inverse. We will get there, but you need the kind of idea of an inverse. So we get a statement here, J is not invertible. And a terminology we might use, J is singular. Okay, so how can we tell if a matrix has an inverse? Can a matrix have more than one inverse? So we're going to answer the first question. The second probably needs a bit of a technical thing, but let me just answer it. The answer is no, you can't have more than one inverse. If we know, how do we find the inverse? In terms of the second question, if you have two inverses, it's not too difficult to show that they have to be the same. Okay, so let A be a 2 by 2 matrix. Now what you have to do is find a matrix that multiplies by this and gives you the identity. So you're trying to solve A, B, C, D, X, Y, Z, W equal to, so remember, so let's call this A, and essentially we're saying suppose A inverse is X, Y, Z, W. And if you multiply A by A inverse, you have to get the identity. Now here I'm doing A by A inverse. Now really what we're nearly doing there is A inverse by A inverse inverse. But anyway, it doesn't really matter. I can swap these two. In that case, it's not going to matter because A inverse is the same as A inverse A. So we want to find A inverse, that if we multiply A by A inverse, that we get the identity. So if you do that, multiply the thing out on the left, you'll get all these equations in x, y, z, and w. Now they're not easy to solve, but it's a fun exercise to show that this is actually the formula. So given a matrix A, B, C, D, the inverse of A inverse, is given by this formula. Now the only problem with this formula is this bit. So we said on a previous page, you can divide by any non-zero number. You cannot divide by 0. So 1 over 0 is undefined. For similar reasons, actually, as, for example, the matrix of 1s has no inverse. Dividing by 0 is to undo multiplying by 0. But loads of non-zero numbers are sent to 0. So for example, 5 by 0 gives you 0. And how do you multiply the number 0 to get back to 5? You can't do it. So that's why you can't divide by 0. So if this number in green here is 0, then the matrix is undefined. Now this thing is called a determinant. And basically the crack is, if that number is 0, this formula does not work, and you can show that there's not some other formula that works. Now we will be explaining, I think on the next page, why if the determinant is 0, it doesn't have an inverse, well, to a degree. So if the determinant of A is 0, then A inverse is undefined. For example, now we've seen something like this AD minus BC before, actually, because it's right down diagonals minus left down diagonals. And you might have heard me using the phrase determinant in the previous chapter when we were calculating the cross product of vectors. And there is a relationship. So right down diagonals here is 1 by 1 is 1. Minus left down diagonal is 1 by 1 is 1. And you do right down diagonals minus left down diagonals, and you get 0. And that shows that the matrix of 1s is not invertible. There's no nice formula for the 3 by 3, but there is a method, but we're not going to be examining it. Okay. So this is how you're going to find the inverse of a 2 by 2 matrix. Okay. We seem to haven't said. Okay, so I think we're going to get back a bit later on, maybe next week or the week after, and explain what the determinant actually represents. The moment it's just some numbers, but actually we can do a little more, but we won't do that yet. Okay, so I think we're just going to do this example here. So given the matrices, so we've got I3, which is the 3 by 3 identity, so that's like the number 1. Got a matrix A there, a matrix B, a matrix C. So show carefully that 2 times I3 times A is 2A. So let's do that. So first we'll find 2I3. Now remember, multiplying a matrix by a scalar, everything gets multiplied by 2, and 0 by 2 is 0. So you end up with 2, 2, 2 along the diagonal, and zeros everywhere else. And now we're going to multiply that by A. So therefore, 2I3 times A is equal to 2, 2, 2 times A, which is 1, 0, 3, 4, minus 2, 3. Now we must analyze this using sizes. So this is a 3 by 3 matrix, and this one, A, has 3 rows and 2 columns. We can multiply these together. These numbers match, and we're going to get out a 3 by 2 matrix. So let's set up our 3 by 2 matrix. 3 rows, 1 row, 2 rows, 3 rows, 2 columns, 1 column, 2 column. So now we're going to start multiplying rows of 2i times columns of A. So first row, first column, and there's so many zeros it actually becomes quite easy. So I'm going to multiply this row by this column. So you get the 2 by the 1 is 2, but it's 0 by 3 is 0. Maybe I will throw them in. Plus 0 by the next thing is 0. Now let's look at the next one over. So it's the same row, but the second column. So you're going to get 2 by 0 is 0, plus 0 by 4, plus 0 by 3. Now in the second row, first column, second row by first column, 0 by 1 is 0, 2 by 3 is 6, plus 0 by minus 2 is 0. And then row 2, column 2, multiply row 2 by column 2, 0 by 0 is 0, plus 2 by 4 is 8, and plus 0 by 3 is 0. And now the bottom left is row 3, column 1, so I multiply row 3 by column 1, and you're going to get 0 by 1 is 0, plus 0 by 3 is 0, plus 2 by minus 2 is minus 4. And then the bottom one then is row 3, column 2, 0 by 0 is 0, plus 0 by 4 is 0, plus 2 by 3 is 6. And we'll tidy that up. So it gives us 2, 0, 6, 8, minus 4, 6. And hopefully it's kind of easy to see that that's actually equal to 2a. But it says carefully do it, so we'll carefully calculate 2a. So 2a, seems to be loads of space here. Oh, that's okay. So just zooming out, look at a there. I have a copy of it here. That's a there. So I'm going to multiply 2 by that. Now a scalar by a matrix, you multiply everything by 2. So 2 by 1 is 2. 2 by 0 is 0, not 2. 3 by 2 is 6. 2 by 4 is 8. 2 by minus 2 is minus 4. And finally 2 by 3 is 6. And is that the same as what I have previously? Yes, it is. So I have 2a is equal to 2a3 times 8. So that's part 1. Okay. Next thing is find b cubed. Now, what b cubed isn't, so you don't just cube all these things. So you don't do 1 cubed, 2 cubed, 3 cubed, minus 1 cubed. It's not that. What does cubing mean? Cubing means b by b by b. I'm going to have to pause and just write this thing down. So this question, b cubed is b by b by b, which is b squared by b, which is the same as b by b squared. What we can do is first find b squared and find it carefully. So b squared, you should write out, is b by b. Now, b from the previous page is 1, 2, 3 minus 1 by 1, 2, 3 minus 1. We'll do our analysis of the size. 2 by 2 by 2 by 2. We will note that the middle numbers are the same, so we can multiply them together, and we're going to get out a 2 by 2. So this is equal to 2 rows, 2 columns, and off we go. And hopefully at this stage, if you haven't figured out the multiplication, it's probably a good idea to actually stop and do some exercises from the previous section, because otherwise you're just more lost, okay? Or even watch some of the previous lectures. Okay, so up here is row 1, column 1, row 1, column 2, row 2, column 1, row 2, column 2. And you take the row of this by the column of this. So off we go. I'm going to go fairly fast. 1 by 1 is 1, plus 2 by 3 is 6. And next one, 1 by 2 is 2, plus 2 by minus 1 is minus 2. Next one, 3 by 1 is 3, plus minus 1 by 3 is minus 3. And then 3 by 2 is 6, and plus minus 1 by minus 1 is 1. So we end up with the matrix here. Oh no. We end up with the matrix 7, 0, 0, 7. Now what you can do here, if you want, is there is a kind of a nice cheat, not a cheat, but a nice way of finishing this off. We'll do it up the top here. So look at b squared. B squared is equal to, it's actually 7 times the identity, the 2 by 2 identity. And therefore, b cubed is equal to 7 times the identity, which is b squared, times another b. And the identity by b is just b. So you get 7 times b, which will be just 7 times b, which will be 7 by 1, 7 by 2, 7 by 3, 7 by minus 1. So we are going to find that's the answer. So there is it's not a cheat, it's a shortcut. Now we will carefully find, we'll do it kind of, we'll multiply that thing by b again, but that would have been the clever way to do this. So anyway, b cubed, we said it was b squared by b. We found b squared to be 7007, and b we've got is 1, 2, 3, minus 1. We can, as before, analyze the sizes 2 by 2, 2 by 2. We can make sure the middle numbers match. 2 by 2, 2 by 2. So we're going to get out a 2 by 2 matrix, 2 rows, 2 columns, and carefully multiply rows by columns. So up the top left corner, that's row 1, column 1. Row 1 by column 1, I get 7 by 1, which is 7, plus 0 by 3, which is 0. The next one is row 1, column 2. 7 by 2 is 14, plus 0 by minus 1 is 0. Then 0 by 1 is 0, plus 7 by 3 is 21. And then the bottom right corner is row 2, column 2, row 2 by column 2, 0 by 2 is 2, 7 by minus 1 is minus, excuse me, that's not right. 0 by 2 is 0, plus 7 by minus 1 is minus 7, and we'll tidy this up. And we get 7, 14, 21, minus 7, as promised, the same as the shortcut. Okay. Next question then is to find C transpose C, where C is this matrix up here. So let's go. So C transpose C. So C transpose C. Now what I'm going to do is I'm going to leave space here for C transpose, and I'm just going to write down C here. So C was 0, minus 1, 1, 0. Okay. So what we should do here to find the transpose of C is the first row becomes the first column, and the second row becomes the second column. So instead of first row 0, minus 1, first column 0, minus 1. Instead of second row 1, 0, second column 1, 0. So let's just be clear here. This is the matrix C taken from the question, and here's its transpose. Now if we want to multiply these together, let's analyze the sizes. 2 by 2 by 2 by 2. Now it might seem like overkill, but I just think this is kind of a good habit. You don't have to do it, of course not. But I don't find it any problem to do, to be honest. And I'm trying to go as fast as possible. So 2 by 2, 2 rows, 2 columns. And we go through each cell and we say what row, what column, multiply that row by the corresponding column. So up here is row 1 by column 1, row 1 by column 1. 0 by 0 is 0, plus 1 by 1 is 1. Then over here is row 1, column 2, so 0 by minus 1 is 0, plus 1 by 0 is 0. Down here we're looking at minus 1 by 0 is 0, plus 0 by 1 is 0, and the other one we're looking at minus 1 by minus 1 is 1, plus 0 by 0 is 0. So we're ending up with the identity. This is the 2 by 2 identity. Now the question is, the next question then is to find the inverse of C, hence or otherwise. Now the hence bit is you've multiplied C transpose by C, and you've got the identity. Now that what matrix do you multiply C by to get the identity is the inverse. So you can just say that the inverse of C is the same as the transpose of C, which doesn't happen in general. I think one of the reasons you study the transpose is there's a certain type of matrix. I think it's called, I think, a unitary or something, and its inverse is equal to its transpose. And inverse is very difficult to calculate. Now 2 by 2 it's no problem, but like you get up to a big matrix, it's very, very difficult. But for nice matrices, which occur in some applications, the inverse is just the transpose, which is very, very easy. And I think that's why you study it. I'm actually not 100% sure. But we will use the formula just to use it. So the formula says that if you have a matrix A, B, C, D inverse, if you want to find the inverse of that, you do 1 over right down diagonal minus left down diagonal. You swap the A and the D, and you change the sign on the off diagonals. So let's do that with C. In particular, C, which is 0 minus 1, 1, 0, inverse, is equal to, so we'll do the determinant. So the right down diagonal is the 0 by 0, 0, minus the left down diagonal is minus 1 by 1, which is minus 1. And then you swap the things on the right down diagonal, so instead of 0 and 0, it's 0 and 0. And then, okay, I've done something stupid down below. We'll get back to that. Hopefully you've noticed how stupid it's been. And then you change the signs on the other diagonal. So instead of minus 1, it's plus 1. Instead of plus 1, it's minus 1. So I've just used the orange formula there. Now the on the bottom, 0 minus minus 1 is 0 plus 1, which is 1. And 1 over 1 is just 1. And of course, multiplying by 1 makes no difference. So this is 0, 1, minus 1, 0. Now, I've made a total dumbass of it because I said down here, I've incorrectly said that C transpose is the identity. That's not right. Here's C transpose. So apologies about that. C transpose is 0, 1, minus 1, 0, which is the same as what we got there. Now what we're going to be doing, we're going to start looking at abstract equations, matrix equations, and using inverses to solve them, and then we're going to solve applied problems using inverses.